Introduction to Artificial Intelligence. Let's talk about AI. I want to start from industrial revolutions. So we've been experiencing a couple of industrial revolutions. The first one is based on the steam power, and the second one is based on electricity. Okay, and then the third one is based on the computer. So these revolutions have their own keywords. And how about fourth? These first and second and third revolutions were defined afterwards. But we are in the middle of the fourth revolutions. So it's really hard to define the fourth industrial revolution. But there are a couple of keywords to define fourth revolution. So IoT and AI and robotics and big data. So we have a couple of keywords to define fourth revolutions. Many CIOs and CTOs worldwide, they set a couple of keywords. So these are the keywords to define the industrial revolution. And as you can see here, we have robotics and big data and AI and Internet of Things. But among all these keywords, AI is actually at the center of word cloud. Okay, and deep learning and cognitive computing and NLP and machine learning and autonomous vehicles, all these keywords are strongly connected to AI. Then what is AI? So AI can be defined in many different ways, but roughly speaking, AI is an intelligence exhibited by a machine. Okay, and it is about simulation of human intelligence by machine. And it's all about cognitive phenomena in machines. It's basically the same things. And AI is about the learning and problem solving. So which means it is about high level thinking and the reasoning. So I think you might have heard about Pavlov's dog. He can learn some things, right? So, but that is not the learning that we are interested in AI. Okay. And in a broad sense, all creatures have intelligence, but we focus on human intelligence. Basically, we focus on human intelligence because human develop AI, and also AI is evaluated by human intelligence. And the goal or direction of AI is also human intelligence. So we focus on human intelligence. And we consider AI as tools. Some people might have some fear that we might have to fight against AI in future. But at least in this class, we focus on AI as tools. And AI can help us like a knife or a vehicle. So we don't fight against a knife or a vehicle, right? Our running ability is worse than vehicle if we're interested in the speed. So we don't compete. We don't fight against a vehicle. We just use it. Likewise, we don't fight against AI. We use AI as tools like image recognition or speech recognition and language translations. We just use them. Okay, now I want to define some terminologies. Okay, so I think you might heard a lot about the weak AI and strong AI from news articles and TV, but actually, the strong AI and weak AI, these terminologies were defined in slightly different ways. So let me describe what these are first. Actually, John Scholl proposed a strong AI in this Chinese room argument. So he actually defined strong AI and weak AI based on the understanding. So if the machine understands Chinese language, then it has a strong AI. But if it just simulates the ability to understand Chinese, then it is a weak AI. So when we build up a room, Chinese room like this, and there is one person out there, and he passed some letter, then this guy actually look at the letter, and then there is a dictionary or mapping kind of book, and based on this mapping book, whenever he sees some letter, then he find another letter, and he drew that letter and then he put it out. Then from outside of this Chinese room, the people might think that there is one person who understands Chinese, but John Shaw said there is no one who understands Chinese in this room. Okay, that's Chinese room argument. So based on his argument, he said strong AI is false. We cannot build up a strong AI. So strong AI is perfectly false. And the difference between the strong AI and the weak AI is based on the understanding something. Strong AI understands something, weak AI simulates something. Okay, so if you look at this figure, this guy said he drew one pipe, and he said this is not a pipe. So I think there is some kind of analogical kind of comparison between these two arguments. Okay, so this is not a pipe, this is a picture of pipe. Okay, so likewise, if we build up some machine which is intelligent, equivalently intelligent to human intelligence, but still this is not a strong AI, it's just a simulation. That's what John Shaw said. But there is another side of this story. Daniel Dennett and John von Neumann, they actually said the mind is just a machine. There's no strong AI and weak AI. There's no difference between these two. Okay, so human mind is also just a machine. So if we make a machine which can behave equivalently to human, then that is enough. There's no difference. Okay, so when we develop AI, probably pretty much we follow this kind of perspective. In the previous slide, we talked about the weak AI and strong AI. Now in this slide, we talk about applied AI and general AI. And in news articles, sometimes and many times, they abuse these terminologies. So they use strong AI to indicate the general AI. So there is no difference in news articles, but technically, applied AI is something like this. So AI can solve one specific problem. Okay, so smart car or speech recognition or translations. Okay, so AI can solve one task. Okay, it's a specialized. But in the movie, SF movie, you can see some general AI. So this AI can do many things. They can read the emails and they can understand the environment, and they can understand the people's emotions, and they can communicate. So they can do all kinds of things. It looks like they are intelligent, really intelligent. Okay, so that is a general AI or artificial general intelligence. For short, it's AGI. But people use strong AI and general AI to indicate the same things many times, but technically it's different things. And Yan Kun, who is one of the godfather of deep learning, he said there is no such thing as AGI. And some people, people might have different opinion about the AGI. Historically, there have been two different approaches to achieve AI, or computational theory of mind. Since we understand that a mind is a computer, so the question is what kind of computer it is. So historically, two different types of computer have been proposed. Okay, first one is based on the computationalism, and second one is based on the connectionism. And in computationalism, thoughts are computation on symbols, and in connectionism, the informations are represented on neurons and networks. So recently, deep learning is actually based on this connectionism. Okay, and in computationalism, the modeling is symbolic, because all the computations are based on the symbols. But in connectionism, we actually represent all the informations on the neurons. So the modeling is actually low level. Okay, and since we are computing something on symbols in computationalism, so it is interpretable. So we know what's going on in the model. But in the connectionism, we don't understand exactly what's happening, even though we can calculate the representations, but it's really hard to understand what it is. And as I said, in connectionism, we have neural networks. In computationalism, we have Turing machines and some other logical computational algorithms. And these are in competition, but also at the same time, they are compatible. So deep learning is based on the connectionism, but it is trying to embrace computationalism. It tries to include some symbols in the neural networks. Okay, so now we understand what is AI and what kind of approaches we have. In engineering, without the evaluation metric, we don't know how to build up a system. We don't know how to compare which one is better than the others. So we need some evaluation metric. Likewise, for AI, we need some evaluation metric, how much intelligent it is. Alan Turing was the first to propose a new evaluation of AI, which is Turing test, also known as imitation game, and it is all about linguistic intelligence. Actually, it checks if machines' behavior is indistinguishable from humans. So this person is communicating with the computer and also communicating with the other person, and if this person gets confused who is who, then we can say, oh, this computer passed the Turing test. Okay, this is a simple idea, but still we can use this kind of idea a lot. Like when we have a machine translation model here, and it translates some sentences, and we have some person, expert translator can translate some sentences, and then the third person actually look at these two sentences, and if this person cannot tell which one is which, then we can say, oh, this system passed the Turing test. Okay. As I said, the Turing test is just a linguistic intelligence, because this person is communicating with computer based on the keyboard. Okay, and this person is communicating with this person based on the keyboard too. So we cannot use any other information like smells or accent or anything else. Even though the linguistic intelligence is quite important, but that's not it. Okay, so Wozniak actually proposed another test, which is coffee test, which is more about general intelligence. It's a simple task. When we ask a robot to give us a cup of coffee, then if the robot can do that, then it passes the coffee test. But coffee test sounds really simple, but it's not as simple as it sounds, because the robot should understand our speech, and it should understand our language, and it should figure out where a kitchen is. Okay, and then it should figure out how to get there, and then when it gets there, then it should figure out where is coffee and where is water, and there are lots of activities there, so it's not that simple. So if the robot can give us a cup of coffee, then it's really smart. Okay, this slide is about the level of analysis for intelligent systems. So actually, David Marr proposed this hypothesis. He said there are three levels, independent levels, like this, to implement intelligent system. Okay, so in the intelligent system, we have implementation level, or physical level, or algorithm level, or computation level. Okay. So in the implementation level, artificial intelligence and human intelligence are different, right? Because our intelligence is based on our biological brain, and artificial intelligence should be based on some silicons and chips, so it's different. As long as we have same kind of algorithm level, then we can achieve same kind of intelligence. Or if algorithm level is too much, then we can achieve the same kind of computational level. Then we can achieve same kind of intelligence. And Thomas Poggio actually added a learning layer. Okay, so intelligent system can learn. This hypothesis is based on the independent levels, but actually they are not. So it's kind of assumption, approximation to implement intelligent systems. But our human intelligence is way much more complicated than just independent hypothesis. If you took a data structure class, then you know what I mean. So when we implement some sorting algorithm, the performance of the sorting algorithm is based on the memory hierarchy and architecture. Okay, so if we have a really good memory system, then we can implement sorting algorithm based on the memory systems. But if the memory system is terribly poor, then our algorithm should be based on just more computations. So these are not independent, but if we have these approximations, then we can achieve some intelligence. And recently, there have been lots of arguments and debates about superintelligence, and Nick Bostrom actually proposed 5 paths to superintelligence. First one is bootstrapping from child machine. So we have a seed AI, and the seed AI can iteratively enhance itself. So the machine need not much resemble a human mind, which means we can have a super intelligence, but this intelligence is quite different from human intelligence because it evolves by itself. Okay, and the next one is brain emulation. So theoretically, there's no problem. We have lots of equations and algorithms to implement our neurons, but practically it's not possible yet. Okay, so we emulate the brain not in the level of atom or molecules, but in the neuronal level. Okay, and knowledge about which neuron is connected to which neuron is not enough. And extra information about the connections are necessary but not yet available. If we can emulate our brain, that is equivalent to our brain. So we have human level intelligence. Then once we have a human level intelligence, then it's easy to get a super intelligence because this machine doesn't need any break. It can evolve. It can get better and better without any break. Okay. Or biological cognition would be possible based on genetic selection and some intervention, which is really a problem politically and morally. Okay. And the next one is brain computer interface. So we can enhance ourselves with a computer so that our intelligence gets smarter and smarter. Okay. And or networks and organizations. One computer is not super intelligence, but if we organize a lot of computers together, then we can have super intelligence based on these collections.